Let's talk about type 1 and type 2 errors. The drug Avandia is used to treat type 2 diabetes, but a 2007 article in the New England Journal of Medicine indicated that the drug might increase the risk of a heart attack. Of all people with type 2 diabetes, one would expect 0.360% of them to suffer a heart attack during a 7-week span. Suppose that in an overall sample of 5,000 type 2 diabetes patients taking Avandia, 25 people had a heart attack during that 7-week span. A. Find the null and alternative hypotheses. Okay, again, the null hypothesis means no change, no difference. Since we're dealing with proportions, our null hypothesis is going to be of the form p equals p0, always has an equal sign. The alternative hypothesis means there is a change, there is a difference. And since we're dealing with proportions, the alternative hypothesis will be of the form p is not equal to p0, or p is greater than p0, or p is less than p0. Okay, in this case, our null hypothesis is that the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span is 0.00360. Again, no different from anyone else. Avandia doesn't make a difference. That's what the null hypothesis is about. We'll state it this way, symbolically. Let P equal the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span. The null hypothesis is that P equals 0.00360. Okay, our alternative hypothesis is that P is greater than 0.0036. We choose this as the alternative hypothesis because we want to test the hypothesis that the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span is greater than 0.006. That's what we were told, so that's what we choose as our alternative hypothesis. Okay, so there's P, there's how we'll define it, there's our null and alternative hypotheses. So let's calculate the test statistic, Z. Here, P hat is the proportion of successes in the trials, although, again, getting a heart attack is really not much of a success. That would be 25 divided by 5,000. P0 is the conjectured value of P in the null hypothesis, and we can see that's 0.0036. Okay, we calculate the test statistic, plugging in everything. P hat 25 out of 5,000, P 0.00360, plug that in top and bottom, and in this case is 5,000. We end up with 1.653. And now let's draw our conclusion. Okay, do we reject or fail to reject H0? Here's basically, these are the guidelines we have for our rejection regions. In this case, our alternative hypothesis is that P is greater than P0. So the rejection region is going to be of the form of Z is greater than Z star. Oh my goodness, what's Z star? Well, here are the values of Z star for two-sided hypothesis tests. Here's the values of Z star for one-sided hypothesis tests, which is what we have here. In this case, since we have a 95% confidence interval, we weren't told, we'll just assume that our critical value is 1.645. Okay, since our alternative hypothesis is one-sided and of the form P is greater than P0, we reject the null hypothesis if the Z-score is too far to the right. In other words, if Z is greater than 1.645, and that's what we saw a moment ago here on this slide. We reject if Z is greater than Z star. In other words, Z is greater than 1.645. Okay, so our Z-score is 1.653. Oh, that is so close. It's greater than 1.645, so we conclude that the null hypothesis is false. We reject the null hypothesis. Find the p-value. What's the p-value? Again, the probability value is the probability that we would get a result this extreme, or even more extreme, if the null hypothesis were true. If the null hypothesis were true, the probability that we would get a z-score of 1.653, or even more extreme, is, well, let's look at the chart. In this case, if the alternative hypothesis looks like this, the p-value is the area to the right of z. So the p-value, the area to the right of z, let's see, we had z equals 1.653, so the area to the right of z is going to be normal CDF, 1.653, 10. 10 is playing the role of infinity. I mean, once you're at 10, you may as well be at infinity. So that's the probability that z is greater than 1.653. We get 0.0492. That is our p-value. So again, the p-value is 0.0492. If the p-value is less than 0.05, we reject the null hypothesis because there's less than a 5% chance we would obtain a result this extreme, or even more extreme if the null hypothesis were true. If the p is low, the null must go. Okay, so again, p is the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span. We reject the null hypothesis. So let's state our conclusion. When our p-value is, this is what we do when our p-value is much smaller than 0.05. This is what we say when it's near 0.05. This is what we say when it's much greater than 0.05. Here we have it's near 0.05. There is some evidence to conclude that, and then we state the alternative hypothesis. So we reject the null hypothesis. There is some evidence to conclude that the proportion of type 2 diabetes patients taking Avandia who suffer a heart attack over the 7-week span is greater than 0.0036. But to be honest, it is so close to 0.05. We don't want to say, oh, it's less than 0.05, so we're going to reject it. Yeah, we do reject it, but we just say that there is some evidence. We don't want to get hung up over exactly doing it at 0.05. Our p-value is 0.0492, and it's close to 0.05. Why don't we just play it safe and choose 0.01 as the cutoff? Well, in trying to avoid one error, we might cause another error. We traditionally choose 95% as our confidence level. If the null hypothesis is true, there's a 95% chance that we'll accept it, and consequently a 5% chance that we'll reject it. That is what we call a type 1 error. A type 1 error is rejecting the null hypothesis H0 when H0 is true. And the probability of a type 1 error, that's what we call alpha. That's our level of significance. So in this case, our probability of a type 1 error is going to be 0.05. So that's our level of significance, alpha. Again, if you have a 95% confidence level, that means alpha is 0.05, 5%. And again, that's the probability of rejecting the null hypothesis, given that the null hypothesis is true. So in the context of this problem, rejecting the null hypothesis, given that the null hypothesis is true, that's like concluding that p is greater than 0.0036, when really it's equal to 0.0036. What's the problem with that in the context of the problem? You're concluding that this drug is increasing the risk of a heart attack, but it's not. So what you're going to do is you're going to yank the drug from a market because you're concerned that it's causing heart attacks when it isn't really. That's not an error you want to make. So you got to be careful about those things. So again, 95% of the time, if the null hypothesis is true, 95% of the time you'll get a result in here. Even if the null hypothesis is true, 5% of the time you'll get a result out here, and that would be called type 1 error. This would lead you to reject the null hypothesis, even though the null hypothesis is true. Conversely, a type 2 error is failing to reject the null hypothesis when the null hypothesis is false. The probability of a type 2 error we call beta. And again, that's the probability of failing to reject H0 when H0 is false. In the context of this problem, you're concluding that P is 0.0036, even though the null hypothesis is false, even though the probability P is greater than 0.0036. So in other words, you're concluding that the drug is safe. It's not really increasing the risk of a heart attack, but it really is. So you probably should yank that drug off the market unless there's no alternative for people. Here's the situation we've got. So this is the real value of P. I mean, we're getting a result that's, at least based on our survey, that indicates that the null hypothesis is true, when really the null hypothesis is false. By the way, the power of a test is 1 minus beta. In this case, beta is the probability that you fail to reject H0, given that H0 is false. 1 minus that is the probability that you actually do reject H0, given that H0 is false. So the power of a test is the power to sniff out a false null hypothesis. In the context of this problem, that's concluding that P is greater than 0.0036 when it really is greater than 0.0036. In other words, it's the probability that you can sniff out that bad drug, and it really is bad.